Bismillahirrahmanirrahim. We'll continue the second session of sampling, and then inshallah we'll start the first session of we'll continue the randomness second session, and then inshallah we'll start today the first session of sampling. Last time, the last thing that we discussed was, I think, Monty problem. Remember? The car and the two goats, and we were done with that. Now we'll go through quickly some basic and very important rules of probability. So basics, the lowest value of any probability, of course, is 0, which means that the chance of an event to happen is 0, is impossible. That's what we mean by 0 probability, that an event cannot happen. On the other hand, when we have an event that has a probability of 1, that means it is certain that this event occurred or will happen. Complement. What do we mean by complement? If an event has a chance 70%, then 30% it will not happen. Okay? So 30% is the chance that it will not happen, which means 1 minus the probability that it will happen. And this is what we call complement. So that's the complement probability. Okay? So an event can happen with probability P. It will not happen with probability 1 minus P. Equally likely outcomes. If we have an experiment and all the outcomes are equally likely, then the chance of an event, we can compute the probability that an event will occur by just counting. By counting the outcomes that make the event happen over the total number of outcomes. So that's what we call the counting rule. That's assuming that all the outcomes are equally likely, then just by counting the number of times that event can happen, we can compute the probability. It will be the number of times that the event, the number of outcomes that make the event happen over the total number of outcomes. Now here's a question, and that I think a basic question that we work on for the first half of the lecture. I have 3 tickets, red, blue, and green. I shuffle them and draw 2 tickets at random without replacement. Without replacement. So I will draw 1. Then I will do another one without replacement, without returning back the first one that I picked. The question is, what is the chance that I get the green ticket followed by the red ticket? What is the chance? When we say chance, what do we mean? The probability. Okay, chance and probability, that's the same thing. So what is the probability that I get the green ticket followed by the red ticket? So let's do it together in a specific way here. Okay, so we have red, blue, and green, right? Okay, so let's make this down. Okay, we have red, blue, and green, and we want the chance that I get green, then red. So I need green, then red, then red. Okay. Now, if I want to solve this by counting, we just mentioned that to get the probability of that event, we need to know what are the outcomes that will lead to that event, divide that by the total number of outcomes. So what are the all possible outcomes here? All possible outcomes of this experiment. So we can get red, then blue, red, then green, blue, then red, blue, then green, right? Then green, red, green, blue. These are all the possible outcomes, right? Right, Mariam? Okay, so these are the six outcomes, right? Okay, how many of these are the outcome of the event, for the event that we are talking about? Just one, which is green, then red, this one, right? So that means that the chance of getting green and red, then red, is 1 over 6. 1 over 6, right? By counting, it's just one outcome, and we have 6 possible outcomes, then the probability is 1 over 6. Okay, now let's do it in a different way. Let's say that we will draw first. Here we want to get green then red, right? Okay, so let's see what is the probability that to get green first. 1 over 3. Very good. So the probability to get green first is 1 over 3. Okay. Now, we got green, right? What is remaining? Red and blue. Okay. Then we want to compute now the probability that we will get red. So what will be the probability now that we get red? 1 over 2. Okay. So red second is 1 over 2. Sorry, 1 over 2. Okay. Then the probability to get green first and red second is what? 1 over 3 times 1 over 2. Right? Right? So green first is 1 over 3. Red second is 1 over 2, right? So getting both, okay, is 1 over 3 times 1 over 2, right? So here, what's going on here? The event has 2 sub-events. We'll have to do both, right? We'll have to do the first, then the second. So we compute the probability of the first times the probability of the second given the first, given that we are done the first. Okay? So what we did here is called the multiplication rule. The multiplication rule. Okay? The multiplication rule, we use it when we have steps in our experiment or in our event. Okay? And we have to go through all of these steps. It's like conditions. Okay? We have to get red first, then we have to get, you have to get green first, then we have to get red second. Okay, when we have something like this, then we multiply these probabilities. So this is called the multiplication rule. And here is another picture that's showing this concept. Okay, so let's say that we will do this experiment on 6 students. Okay, so all of them will have 3 tickets, and they will pick randomly one of them. Okay, since the probability we just mentioned that the probability of getting green first is 1 over 3. So out of 6 students, how many? Mostly how many students will get the green one? 2, right? 2 out of 6, which is 1 over 3. So 2 out of 6 will get green, and the others will not get green. So they will be removed from the experiment. They will leave. It's like they will leave the class. Okay. Now what is remaining is these 2, right? These 2 students. Okay, now, among these 2 students, how many, so among the population here, among these 6 students, 1/3 will get the answer, right? Will get the right thing. Now, among these 2, if I ask them now, pick another one from what is remaining, okay? And we will see how many of them will get red next. Okay, so we have 2 tickets. Okay, getting one of them will have the chance of 1 over 2. Okay, so it's a fraction, so it's 1 over 2 of 1 over 3. We get rid of these 2/3, we have this just 1/3, and among the 1/3 we have 1/2. So it's a fraction of a fraction. It is 1/2 of 1/3. And that's why we multiply here. 1 over 3 times 1 over 2. Because it's half of the third. Okay? Is that clear? So that's an explanation of what we call the multiplication rule. So in the multiplication rule, it's the chance that 2 events A and B both happen, which is the probability that the first one happens times the probability that the second one happens, given that the first one has happened. And since it is a fraction of a fraction, okay, then the probability that we will get eventually should be smaller or higher than the probability of any of these two. Smaller, right? Smaller generally, unless they are 1. Okay, but generally it is less than or worst case equal to the probability of both of them or each of them. Okay, so the answer is less than or equal to each of the two chances being multiplied. Remember, it's a fraction of a fraction, and fraction is less than or equal to 1, right? So eventually the probability will be less than or equal to each of the two chances being multiplied. So if I have more events, okay, it's like having more conditions, which means that the probability will, as we are adding events and the conditions, the probability will increase or decrease. Will decrease, of course, well, because we are taking fraction of a fraction of a fraction, right? Is that clear? So the probability, of course, with more conditions that we have to satisfy, it is less likely that we satisfy them all. Okay, so as we are adding events, then the probability will decrease. Now here's another question. I have the same 3 tickets, red, blue, and green. Now I will shuffle them and draw 2 tickets at random without replacement. How is that different from the previous one? Nothing different, right? It's the same thing until we know the question. The question is, what is the chance that one of the tickets I draw is green and the other is red? Is that different from the previous one? What is the difference here? I'm not asking for the answer now. What is the difference between this question and the previous one? The order here doesn't matter. Okay? In the previous one we said we want green first, then red. Here we said what is the chance that one of the tickets is green and the other is red. Okay? So let's see how we can do that. So now we need red and green, right? Is it red and green? Yes. We need green and red without paying attention to the order. Fine. If we use the counting rule, then what will be the probability? How many of these 6 possibilities are satisfying this condition? 2 of them, right? So this one and this one, right? So that means that the probability now will be 2 over 6. Will be 2 over 6. Okay? Okay? Fine. Now, we can also say that, questions? We can also say that we can get this outcome in one of 2 ways. We can either get red first, then green, or green, then red. Type. What is the probability that we get green, then red? 1 over 6. What is the probability that we get red, then green? 1 over 6. Yes, we add them. So we don't multiply here, right? We just add them. Why should we add them, not multiply them? Yes, because it's one of them. Because we have 2 possibilities, okay? And one of them only will happen. One of them only will happen. If that's the case, then we use what we call the addition rule. Okay, the addition rule. So we'll add 1 over 6 plus 1 over 6, we'll get 2 over 6, which is 1/3. So if event A can happen in exactly one of 2 ways, then probability of A is equal to the probability of the first one plus the probability of the second way. Okay, it's not the multiplication. Why not the multiplication here? Because these are not 2 events that will happen both. It's just one of them that will happen. Okay? The other one we have to say green first and red second. Okay? Here we are not saying that. We are saying it's either green first or red first. Okay, now the outcome, the answer, or the probability will be greater than or equal to any one of them, right? Now we are adding probabilities, so it will be greater than or equal to the chance of each one individually. What if we have 3 possible ways, not just 2? Generally, not in this question, but generally, if we have 3 ways, we'll add. So that will generalize to multiple ways, right? If we have n ways, then it will be probability of the first plus the second until the last one. Okay? But the main condition here is that exactly one. So the event will happen in one of these ways. We don't know, of course, which ways, but it can happen in any of these ways, but exactly one of them will actually happen. Now the complement. So here we are talking about at least one kind of questions. So let's say that we have 2. We can do that here. Let's say that we have 2 coins. Okay, 2 fair coins. Okay, you know, fair coin will give us head or tail. Now, if I ask you what is the probability that I will get at least one head? Okay, so let's do it by counting. Okay, so how do we do it by counting? We get all the possible outcomes, and then we see which of them will satisfy what we want. So what are the possible outcomes here? I know head or tail, that's just for one coin. For both, we can say we can get head, sorry. So head, tail, head, tail, right? These are all the possible outcomes. Okay. Now how many of these? So we have 4 possible outcomes. How many of these have at least one tail? 3. At least one tail is 3, right? So now then the probability is 3/4. Okay. Now this one means no tail, right? No head, this one. We're talking about at least one tail, right? Okay, so this one has no tail at all. Okay, I'm confused. Sorry. So we're talking about at least one head. Okay, so 0 head is this one. Right? Right. This is just 1. So the probability to get 0 tail, 0 head is 1/4. Okay? Which is the complement of what we just mentioned, right? So we said at least one head. At least one head. Okay? And we found that the probability is 3/4. Now the complement of it, which is 0 heads, is 1 minus that, which is 1/4. Now, so this is maybe easy for this, but if I told you I have a die and I will roll it twice, okay? Now, what is the probability that I will get at least 1/6? 1/6. The roll has from numbers from 1 to 6, right? Right? Let's say 5, not to be confused. Okay? I will roll the die twice. Okay? Each one will give me a number from 1 to 6. Okay? Among these 2, what is the probability that I will get at least 1/5? And I will see from the 2 outcomes that I will get at least 1/5. Okay, how can we do that? Okay? How can we do that? Okay, what do we mean by at least 1? It can be 1, it can be 2, right? Right? So we have 2 possibilities. Either we compute the probability that we will get exactly 1/5, and also the probability that we will get exactly 2 5s. And what should we do with these? Add them or multiply? Add or multiply? Add. Why? Randomly. Why is it add, not multiply? Because it will happen one of these 2 cases, right? So at least one, it will be either Exactly one or both, right? So we have to compute these two and add them. Or it's maybe easier to say it is the complement event of having no 5s at all. Isn't it the case? When I say at least one, the complement of it is no 5s at all, right? Right? And that will be one computation. So it looks like easier. If we can compute this, what should we do to get the other one? Just 1 minus, right? That's because it's a complement. Just 1 minus, right? So what is the probability to get the at least 1 5 then by the second way? Is to compute the probability that we will get no 5. What is the probability that we will get no 5? Why is it 1 over 6? No 5. What do you mean by no 5? It's any number except 5 in the first one and any number except 5 in the second one, right? What is the probability that we will get any number except 5 in the first one? 5 over 6, right? All numbers except 5. 5 over 6 and the other one is also 5 over 6, right? Right? So we'll multiply them now. That will be 5 over 6 power 2. Now what is that probability? It's the probability. No, I'm not. I didn't mean the number. I mean the meaning of it. It's the probability of having no 5s at all. 1 minus, yes, 1 minus this will be the probability that we want, which is at least 1 5. Okay? So complement is nice when we have two ways to compute the probability that we want, but one of them might be much easier to do. Okay? So sometimes this kind of questions, at least one, is easier to do when you think about the other way, when you think about the complement. How is that related to data science? Sometimes when we do a sample from a population, we want to make sure that at least one from a specific group in the population will be in the sample. We want to compute the probability for that. Okay? To make sure that the sample size that we will have a high chance to have someone from that population. Okay? Let me give you an example. Let's say in that class, how many Egyptians are here? Just one. Okay. So 1 out of, I think, 14 or something. Okay. So 1 out of 14. I want to make sure that this one, if I take a sample, this one will be included so that it will represent this minority here. Okay. So I want to compute, if I take a random sample of size 5, for example, what will be the chance that at least one of them will be Egyptian? Okay, so that's it comes a lot in data science, as we will see inshallah later. Now, if I generalize this experiment, so we said that this one now if we do it with the complement, back to the head and tail experiment, if we do it with the complement, it will be 1 minus 0.5 to the power. We have 2 coins, right? It will be to the power 2, okay, which is 0.75. Okay. Now, if I have more than 2 coins, if let's say 3 coins, how that will be different? It will be power 3. Very good. So it will be power 3. Now the probability will be 0.875. So you see, it will increase, right? It will increase as we add more, as we take more samples, as we run the experiment multiple times. Then the chance of having at least one will increase, and that's logical, right? As we get more and more samples, this one will appear eventually. Okay. If I want to generalize this, and here is again the dye experiment. So look at this code and tell me what are we doing. So here, what are we doing here? So we have an array from 1 to 50. Okay. Now we will add a column, actually 2 columns, to a table where the first one will have this array, and the first column, and the second column will be What's this? So this is the probability that we just mentioned, right? That's the probability that we have at least 1, maybe 5, for example. Okay? When we roll the die, that times the number of rolls. Remember, the rolls is from 1 to 50. So each row in the table, let's say the row number 5, row number 7. Okay, in the row number 7, we will get the probability that when we roll the die 7 times, we will get at least 1 5. Okay? Do you understand now what is this doing? Okay, now what should we expect in the second column? So that second column will be the probabilities, right? Okay, as we go down, should the probability increase or decrease? Increase, right? Right? Because as we mentioned earlier, as we add more samples, the probability that we will get one of them to be 5 will increase, right? If we roll the die twice, maybe the probability of getting 1 5 is small, but if we roll the dice 100 times, of course one of these 100 most probably will be 5. Okay? So we'd expect something like this. So you see, in the first row, what is that number? I understand that's the probability, but I mean, what is as a fraction? What do you expect for when we roll the die 1 time? Okay, what is the probability that you will get at least 1 6, 1 5? 1 over 6. So this is 1 over 6. Okay. Then this is 1 minus 1 over 6 power 2. This one is 1 minus 1 over 6 power. Sorry. Okay, so this one is 1 minus 5 over 6. Okay, which is this one is 1 minus 5 over 6. That's the complement. And this one is 1 minus 5 over 6 to the power 2. Remember that we are getting the complement of having no 5s. Okay, and for example, this one will be 1 minus 5 over 6 to the power 7. Okay, so as you see here, the numbers increase. Yes. Sorry? The whole what? The rolls, yes. It will be the power, yes. You see the calculation here, right? So that's the number of times. Now, didn't we say that we get the complement by 1 minus the probability that we will not get any of them, any of the 5s, okay, which is 5 over 6 every time. Okay, so 5 over 6 for the first, 5 over 6 for the second, and so on. You see here the number will increase, and it will get very close to 1 as we add more and more rolls. Okay, isn't that logical? Okay, so by that we are done with this part. Any questions? Good. So let's move on to another session. Okay, which is sampling. So what do you mean by sampling? Any idea? Array? Arranging. Oh no. Finding the sample. No, when forget about probabilities. Okay. When I say I'm sampling. Yes. What do you mean by taking a sample? Some of the, so we have like a population and we are taking some of them. Okay, we are focusing on one of them, or we will be doing something with some subset of them. Okay, so that's what we mean by sampling. So let's do a demo and see what exactly sampling is. So, okay, so we'll work on a data set of flights. So that's a data set on specific year, I think 2015 here, on the flights of a company called United Airlines in the US. Each row here is one flight. You'll see when it was done, and the flight number, and the destination airport. So this is going to, so the source here, the source is fixed, and the destination is different. Okay, so this one is going to HNL and so on. And this column indicates how many minutes the flight was delayed before it took off. Okay, so this flight was delayed 257 minutes. This one is 28. And this one is -3. What does that mean? Yes, it left earlier. Okay, it left earlier. And so on. Okay, so that's the data set. Now, what should we expect when we do this? We'll get all the flights, yes, that are going to this airport, right? Okay, so we'll get something like this. Everything is EWR, right? Okay, now is that a sample? So remember the data set? The data set here has more than 13,000 flights, okay? And here we have this number, but anyway, is that a sample? Yes, it is a sample, right? Is that a random sample? No, why not? Yes, so there is no chance here. There's nothing random here. There's no chance, right? We know exactly what are the rows that we will get, or what are the elements that we will get from the population, right? The population here is all the flights, and we selected some of them, so that's not a random sample. This is called deterministic sample. Deterministic sample. It's very specific. We know what we will get. Okay, deterministic. There's no chance here. There's no randomness here. Okay, so that's clear. How about this one? What is this? So what is this one first? In numpy.arange 0 to number of rows and 1,000. Yes, each 1,000, starting from 0. Very good. So it will be 0, 1,000, 2,000, and so on. Okay, so if we run this, we'll get something like this. These are the rows that we will get. Okay, is that a sample? It is a sample, right? Because it's a subset of the population, right? Is that a random sample? I heard many yeses. Is that random sample really? Why is that random sample? Where is randomness here? There's no chance here, right? We know exactly what we want, right? We want the row number 0, row number 1,000, 2,000, 3,000, and so on. So this is still what type of sample? Deterministic sample. So still this is deterministic sample. Okay, Mish, but given the data set, we are saying give me the row number 0, row number 1,000, and so on. Okay, so if we label them by numbers, halas, there's no randomness. Okay.
So whenever I make like any condition to get the data, so it's get out of the.
If there is no if the chance, if you don't know the chance before you do the sampling, then it's random sample. But now you know the chance, right? Because only the rows 0 and 1,000 and 2,000 will be selected, so there is no randomness. So this is deterministic sample. Right, Amina? Okay, how about this one then? So what do we do here? It will give us back these 3 rows, right? So if we run this, we'll get these 3 rows. Is that a sample? Yes, it is a sample. Is it random sample? No, not yet. Okay, no, it's not a random sample. Is it deterministic? Yes, of course, it is deterministic. Okay, good. Now, look at this one. What are we doing here? So what are we doing in the first line? What are we doing, Marwa? Yes, so it will give me a number, right? One number. The first line will give me one number between 0 and 999, right? It will give me a number. Okay, so now let's say that this number is 17. Okay, now what are we doing in the second line?
We specify this array from the start And goes 1,000 from that point.
So we get, so the step here is 1,000, right? So it's similar to what we did earlier, but instead of starting from 0, we are starting from a random position. Okay, so you understand now what's going on? So if no? Okay. So this line is very similar to what we did earlier when we get 0, 1,000, 2,000. The only difference is that we start from a random position, because start here is random. Okay, so if the start is 17, then we will get rows number 17, 1,017, 2,017, 3,017, and so on. Okay, so let's see what we will get here. So it seems like the start is what? 355 here. Okay, so we started by 355, 1,355, 2,355, and so on. Okay, right. Is that a sample? Yes. Is that deterministic sample? It's not deterministic, right? It's not deterministic because we don't know in advance which rows we will get, right? But still also it's not a random sample, because when we, in a random sample, we need to know in advance the probability of selecting every element in the population and every subset of the population. Okay? Here, we don't know in advance this probability because it depends on the starting position. Once we know the starting position, equally spaced in the data, we will get these rows. So it's kind of mix between deterministic and random. So it's not random. This one is called systematic sample. Systematic sample. So when we have a systematic sample, we start randomly, but then we get equally distant elements from the population. Okay. So for example, here, if the starting point is 17, okay, what is the chance that the sample will have 5 in it? We have the row number 5. If we start by 17, 0. Type. How about 100? No, 100 will not appear also if, I mean, if we started by 17, what is the probability that we will get the row 100 in the sample? Still 0, right? Do we know that in advance? No, we don't. We don't. No, but we don't know where we will start, right? Okay. Because 100 will not appear if we started by 17. We are adding 1,000 every time. So it will be 17, 1,017, and so on. Okay. So some subsets will be 0 and the other one will be 1, and we don't know that in advance. Okay. So that's not a random sample. In a random sample, we know in advance the probability of every element and every subset of the elements to be sampled. Okay, which is not the case here. So this one is called systematic sample. This one is called systematic sample. Okay, so quickly, what is the difference between the deterministic and the random sample? The deterministic sample, it doesn't involve chance. It doesn't involve chance. The random sample, before the sample is drawn, you have to know the selection probability of every group of people in the population. Okay, of course we are saying people here, but generally it is individuals. Can be flights, can be anything. Okay, and what do you mean by group here? Every subset. Every subset. Okay, so in advance, before we draw the sample, we know the probability to get any subset of the population. Okay, so we can calculate it. We don't have to calculate it we don't have to calculate it for every subset because the number of subsets is huge, but we know how to calculate it. If we know how to calculate the probability of every subset in the population to be in the sample, then this is a random sample. Otherwise, it's not. And not all the individuals or groups have to have equal chance, by the way. And it's not the case that it's a condition that every individual in the population has the same probability to be in the sample. It's not a condition. They can have different probabilities. That's okay, still it is a random sample if we know that in advance. Now, one last type of sample Okay, I know that it's the last one more minute and we'll be done. If I came to the class and the first one was whom? I think was Mariam. Okay, so Mariam was here when I came in the class. Now I will tell Mariam, let's have a sample from the students of the class. Okay, well, the sample will be the first 3 students who will come to the class after you. Okay, so the first 3 students entering the class after Mariam is the sample that I will get. Now, is that a sample or not of the students? It is a sample. Is it a random sample?
No, because I don't know who will become
Okay, when can we say that it's a random? It's a random sample when we know in advance the probability of every individual in the population to be in the sample. Do we know that in advance? Maybe some students will used to come late. Maybe some students today are sick and they will not come. Okay, so we don't know that in advance, right? So the probabilities are not known in advance. So this is not a random sample, but we call it a sample of convenience. Okay, a sample of convenience. Okay, so you might think it's a random, but it's not actually, because you don't know in advance the probability of everyone, and maybe you don't even in some experiments, not this one. You don't know even what is the population in advance. So this is what we mean by whoever walks by. And just because you think you are sampling randomly, as some of you did now, doesn't mean that you have a random sample. If you cannot figure out ahead of time what is the population and what is the chance of selection for every subset of the population, then you cannot say you have a random sample. Okay, so quickly, what are the types that we discussed so far of sampling? Deterministic, systematic, sample of convenience, and random sample. Okay, I hope that you know now the difference between all of these 4 types. Yes? No. Systematic starts by a random choice, but then systematically choose some of the population, some individuals from the population. Any other questions? Okay, thank you.